What is cavitation? Welcome to Trimteck. In this video, we'll explain one of the most destructive and fascinating phenomena in fluid control, cavitation. We'll look at what cavitation is, why it happens inside control valves, the damage it causes, and how Trimteck engineers design valve trims to control or eliminate it. If you work with liquid service valves, in power, refining, chemical processing, or any fluid handling system, understanding cavitation is essential to keeping your plant safe, efficient, and profitable. What is cavitation? Cavitation happens only in liquid media, when pressure and velocity conditions inside a valve create vapor bubbles that collapse violently. Here's how it works. As liquid passes through a control valve, it accelerates through the narrowest point, called the vena contracta, where velocity peaks and pressure drops to its minimum. If the pressure at that point falls below the liquid's vapor pressure, the liquid actually begins to boil locally, forming tiny vapor cavities or bubbles. As the fluid moves downstream and pressure recovers, those vapor bubbles collapse or implode back into liquid form. Each implosion is like a microscopic hammer blow, and when millions occur per second, they can literally eat away metal surfaces. That's cavitation, a phase change from liquid to vapor and back to liquid, triggered by pressure drop and recovery inside a valve. Cavitation versus flashing. If pressure recovers above the vapor pressure, the bubbles collapse. That's cavitation. But if pressure stays below vapor pressure, the bubbles never collapse. The fluid remains a vapor-liquid mixture downstream. That's called flashing. Both are undesirable, but flashing is even more erosive because those high-velocity droplets continuously strike surfaces downstream. We'll see that the approaches to engineering a valve for each of these services are very different. Cavitation can often be controlled or eliminated. Flashing is often an inherent requirement of the process and cannot be effectively eliminated without changes to the process conditions. Hydrodynamic versus aerodynamic noise. Both cavitation and flashing create hydrodynamic noise. That's noise generated by collapsing bubbles in liquids. It is often compared to the sound of gravel or marbles tumbling down the pipe. In contrast, aerodynamic noise comes from turbulence in gas or vapor service. We'll explore that topic in another video. For now, we'll focus on cavitation and its effects in liquid control valves. The damage cavitation causes. Cavitation damage is a form of hyper-erosion. Every bubble collapse creates a shock wave strong enough to pit the metal surface. Over time, these pits multiply and connect, wearing away seats, plugs, and cages, or even drilling holes through valve bodies and piping. Cavitation damage is easy to confuse with corrosion, but it's almost always found just downstream of the seating area, where those vapor bubbles collapse. Unchecked, cavitation can shorten valve life dramatically and cause unplanned downtime, leaks, and process instability. Factors that influence cavitation. How severe cavitation becomes depends on several factors. Pressure drop. Greater drops mean greater risk. Time of exposure. Continuous operation accelerates wear. Flow rate. Higher flows intensify cavitation. Materials. Hardened trims last longer. Valve size. Increasing the size of a valve often increases the likelihood of cavitation damage. Allowable leakage. The lower the leakage class of a control valve when it is closed, the more likely it will suffer damage from cavitation. And of course, valve and trim design, the key to prevention. Measuring cavitation potential. Engineers measure cavitation potential using the sigma cavitation index. the ratio of a fluid's resistance to vapor formation versus its tendency to form vapor. Trimteck uses this index, along with decades of lab and field data, to select the right trim, valve type, and material for each application. Trimteck's approach to controlling or eliminating cavitation. At Trimteck, we've spent decades engineering severe service trims that control or eliminate cavitation. Our approach depends on the severity of the service. For mild cavitation, our ST1 single-stage anti-cavitation trim uses mutual impingement, directing vapor jets toward each other so they collapse harmlessly in the center of the cage instead of against the metal walls. For more severe conditions, our ST2 multi-stage trim gradually reduces pressure through a series of small channels and holes, preventing the pressure from ever dropping below vapor pressure. This stage design eliminates bubble formation and drastically reduces hydrodynamic noise. For the most extreme cases, our ST4 stacked disc trim provides up to 10 pressure-reducing stages, handling massive pressure drops while also reducing noise. For flashing service, the approach is one of extending the life of the valve and downstream piping using hardened materials, and displacement technologies like our ST5 Venturi seat ring for flashing service, which directs the flashing flow downstream and away from critical components. Each trim is custom engineered for its service, whether water injection, boiler feed, or corrosive chemical flow, and available in hardened materials such as 400 series stainless steel, Hastelloy, Inconel, Stellite, or Trimteck's proprietary CVD-5B metal-hardened surfaces, which extend valve life by up to 10 times. Cavitation is complex, but with the right understanding and the right valve trim, it's a problem you can solve. At Trimteck, we engineer, design, and manufacture severe service control valves that protect your systems, your uptime, and your bottom line. Visit trimteck.com to learn more, or reach out to our engineering team for help on your next application. And don't forget to like, subscribe, and click the bell for more valve sizing basics. See you next time.